We will approach machine learning on how it really is to developers, because the truth is machine learning is not that difficult when you truly understand it. When you explain it this way, it really seems very intimidating, but it's not really like that. Actually, it is like that, but that's the complicated way of doing it, the complex way of explaining it. All right, let me just get my microphone sorted. Okay. All right, so I will dive straight into the code. So let me get out of this full screen mode. Okay. Now, caveat, I will be doing live coding here in front. You are all developers, you know how this feels. So I will make mistakes. And so when I run into bugs, your job here is to encourage me and cheer me on, all right? So that I don't get depressed and freeze up, all right? So whenever I get stuck, you just clap your hands. Practice. All right, okay. This feels very cheerful. I like this crowd. So one of the tools that we use, or I personally use for running machine learning models or doing machine learning, so before I go to, I keep saying machine learning. So what is machine learning? Machine learning is a subset of artificial intelligence. Okay, artificial intelligence is anything that any form of program or algorithm or computer program that has some sort of smartness to it or intelligence to it. Okay, so it can be as basic as when you're playing against a chess in the computer, and you're playing against a computer. Now, how that was programmed, there are many ways, right? There are many ways. They can program it with if-else statements and all these rules, right? But that's already artificial intelligence. That's already AI. That's rule-based AI. When you're playing Dota 2, right? There is the AI. There's the easy, the hard, and the insane. All right. So I'm not so sure how they program that, but it's definitely not machine learning in the beginning. I think it's like a lot of if-else statements again, rule-based, that if the enemy is this distance, it execute the hardest damaging spell right away and then retreat. Like that is like how they program that. That's already AI because that's already artificial intelligence. Okay. Machine learning, however, is a subset of artificial intelligence where instead of having rules, you give the machine data, right? You give the machine a lot of data, and we call this training data, and then using the data, the machine tries to learn the rules on its own, or tries to learn the patterns on its own. For example, if I gave the machine a lot of pictures of me, and I gave the machine a lot of pictures of Nielsen, stand up, Nielsen. Alright? Now, the objective of the computer, wala man siya ni stand up, pero sige na. The objective of the computer will then be able to distinguish between me and Nielsen. So he'll try to figure out the patterns. So in terms of pictures, so this is pixel data, right? You can see our complexion is fairly the same, but my nose is maybe a little flatter. So the computer will be able to tell that using variety or volume of examples, and then will be able to distinguish the patterns on its own, determine the patterns on its own, and learn this on its own using a lot of training again and again until it eventually gets it right when you show him or show the computer a new picture of Nielsen or a new picture of me. So that is the concept of machine learning. It uses a lot of data, there's no rules. Using a lot of data, volume of data, the computer isn't able to infer the patterns on its own and then be able to create predictions given new data. Alright, so how does this work? Alright, right now, we'll go to Google and we'll see Colab Google. So this is a tool, I'm gonna zoom in. People at the back, can you see? People at the back, can you see or not? Yes. Oh, you can see, good, great. So this is Hello Collaboratory. This is a tool that lets me run code on Google's cloud, and we will use this. I will say new Python 3 notebook. All right. Who uses Python here? Okay, one. Great. But the rest of you, don't worry. Python is like pseudocode. So if you know programming, you'll be able to understand Python, hopefully. So let's give this a title. Let's call it House Price Prediction. Okay. So one day, my boss comes to me. Alright, let's pretend I have a boss. I'm usually the boss. But usually we have a boss, right? Our boss, or for me, my boss is the client. Client comes to me and tells me, Albert, I want you to make a function. I'm like, what function? I want you to create a house price predictor. And I was like, okay. So how will I know what the function, what are the specs? And he'll be like, okay, these are the current house prices. Can you see? At the back, visible enough? Okay, right? Okay, it's good. So house prices equals, I will say, if there is one room, this is one room, the price is 10,000. Okay. If it's 2 rooms, the price is 15,000. If there's 3 rooms, the price is 20,000. And if the 4 rooms, the price is 95,000. And if there's 5 rooms, the price is 30,000. Okay, and then so the job is create a function that given rooms returns price. Okay, so that's our objective. So we have that data. We run that. I'll create a new code block here at the bottom, and I'll say, okay, we'll make our function. We'll call it very house price predictor. Okay, and the given rooms, that's what we get. That's the parameter we receive. We have to return price. So we'll just say, I'm a programmer. I look at this. What should our function be? House prices 1, 2, 3, 4, 5. Okay, 10,000. So I can do it this way. If rooms is equals to 1, return 10,000. If rooms equals to 2, return 15,000. Okay, if rooms equals to 3, return 20,000. If rooms equals to 4, return, how much is this? 25, very good. And if rooms equals to 5, return 30,000. Okay. So then I'm happy. Let's try it out. So I say code house price predictor, and I'll be 1, 10,000. Yay, I'm right so far. Test is pass. 4, 25,000. 5, 30,000. Boss comes and says, okay, try 6. And then you're like, what the? It doesn't work. And like, but you didn't give me data for that. It's like, it's okay, but just like try to predict what it would be. So I'll be like, okay, else return expensive. We can do that. Oh, it doesn't work still. Sorry. We have to print maybe? Sorry, print. None. Why? Thank you very much for the encouragement. Okay, I had to unindent it a little bit. Alright, turns out that 2 spaces here is a tab. Alright, so okay. So, expensive. Your copy really worked. Thank you very much. Now, the boss says, that's not gonna work, Albert. I need a number. I need like a prediction of a number, an actual number. So I'm like, oh gosh, I have to map this thing. Okay, so if it's 10,000, 15,000, it looks like it can be this. So the rules is, the price is actually a function of price is equals to rooms times 5 plus 5,000, right? Are the people in the room okay about it? And the return price. Okay, let's try this one. Let's run this again. So we'll do 1 first. 5,005. There. Very good. Thank you for the good coders. That's why you're Lexmark. Very good. All right. How's pretty? 1 is 10,000. It's correct. Let's try 3. 20,000. That's great. And then let's try 5. If we're still there. Okay. Great. Great. I was even foretelling it. Oh my goodness. This is, by the way, a Google Cloud. Just saying. Cell is already running. Okay, yeah, but not returning. Can I stop you and then I'll run again? For the class. Let's try another cell over here. Print house price equal predictor equals 6. Let's try 6 one. No, actually, this is gonna. Okay, I'm giving you 5 seconds. 5, 4, 3, 2, 1. So I'm going to open something. It's a local version of this. Hold on. Don't be scared. Jupyter Notebook. So that was Google Colab is like an online version of it. I have actually a local version of it. So I have this one. It's called Upload New Python 2 Notebook. So it's exactly the same, it's just not online, it's just local, so I have to install it. The reason why I wanted to show you the Colab is so that you can just automatically just go there and do it, right? But since it's slow for my use case at the moment, we're going to forget that one, we're going to not use this, and we're going to just go here. So I'm gonna copy here, house prices, and then I'm gonna have this one, just transferring my code. Okay, how do you create a new? Insert cell below, okay, there, run that, and then finally print house price predictor, then insert cell below, okay, do that, 30,000, yes. So let's close Colab for now, bye-bye Colab, and then might be insert cell below, we try 6, because our boss wanted us to create a predictor for something that we don't have data for. So it's 6, 35,000. 7, 40,000. I'm happy, give it, boss happy. Yay! Amazing, project success, make a lot of money. Alright? Problem is, in reality, it doesn't look like this. Right? In reality, this is more like 9,000. This one is what? 13,000. This one is 19,000. This one is 27,000. Sorry, 27,000. And this one, 500 house probably would be 35,000. Right? That would be the closer to reality. Sort of, in Cebu, at least, in pesos. So we changed the house prices. So this one, we run this again, and it's no longer true. Right? So now you're looking at this and you're like, oh my gosh, how do I math this thing? Because it's not times 5,000. If it's times 5,000, it's not so close, right? So what we do is, what if we can say, there is something called, we can replace this thing. This one is supposed to be, sorry, tab is there. See, that's why I got a bug a while ago, because the tab is different. Okay, so here we have, I'll enter the comment, we'll say, what if we can replace this one, we call this modifier, alright? So our rooms multiplied by our modifier plus another modifier 2, alright? Okay, so we try to figure this out, and then we say let's pass modifier and modifier 2 here, and then say that, and then let's run 5. Let's just say let's start with 1. Let's go to achieve 9,000, right? 1 room, and then we say 5,000 here, and then 5,000 here, and it's 10,000. Right? So that's wrong. So what we can do maybe is we can just keep on trial and error. See? Very fast, trial and error chamba. Okay. But now we have this value, so this is good values, alright? 9,000 because it hit jackpot here. But for number 2, we have to have 13,000. So we'll try number 2. So let's copy this one. Okay. Number 2. Oh wow, jackpot. Wow, okay, I didn't expect that. But it's okay, so that's a good modifier then. Okay? But for 3, let's see for 3. 17,000. Oh no, we've missed it by 2,000 now, right? So that's a very good modifier. So what should we change it to? Maybe we should make this 17, we want to increase that a little bit, right? By 17, so 19 by 2,000, so maybe increase this by 6,000. So 18, 7,000, no? Now the problem with this is now our modifiers are this, we have to change it also here. So now our values for the other is off, right? So now we kind of have to ask ourselves, that's kind of, we're off here by 2,000, we're off here by 2,000, so we're averaging, but we hit jackpot here, but we're off by 2,000. Can it be that we'll just make it that they're all off by 1,000? Para fair, diba? So we'll be like, okay, let's make this 6,000. So that's off by 1,000. This is also off by 1,000. And this is off by 1,000. So now we're not jackpot all the time, but we're mostly correct or close to the correct, to the real one all the time, based on these two modifiers, right? Now let's go to the third one, to the fourth one. Okay, we go to 4, and we're at 22,000. Crap. Okay, we're off by 5,000 now. So how much should we be off? Maybe we should just be off at the most 2,500. So we'll then go and adjust everything here. Now, this is pretty tiring as a developer, as a programmer, if you program this way. But the good thing about this is we're programmers. We can program these things, so we can do this. So let's try it, okay? What we're going to do is we're going to do a for loop for possible modifier 1 in range from 0 to 10,000. Okay. And then we're also going to do another for loop for possible modifier 2 in range from 0 to 10,000 as well. Okay. And then we're going to say house price predictor 1 this is house 1. Okay, I don't like copy and paste here. House 2. And then we're going to change this first. So this will be possible modifier 1, possible modifier 2. We're out of space, so I'm going to change the variable. So this might make it P. P modifier 1 and then P modifier 2. Okay. P. Are people following so far? Okay, great. Alright. So basically we're going to do house 1. And then we say house 1. Okay, there. House 1, house 2, 3, 4, 5. Okay. House 1, house 2, house 3, house 4, house 5. We delete this one. And then this is 1, 2, 3, 4, 5. Now that we get all the possible, the prices of this, we will then say actual price over here. Let me delete all of this so that we can have a cell delete. Delete. How do you delete? Delete. Edit, delete. Edit, delete. I'm a bad programmer. I forgot all the shortcut keys. Okay. So what we're going to do here is we're going to compare actual versus predicted, right? So we're gonna say actual is equal to actual 1 is equals to house prices 1. Okay, let's test this first before we insert cell above actual 1 so that you can see it, and then print actual 1. Okay, that's 9,000. If we change that, it will become 13,000. Whoops. Actual. So is on. So what? Cell run cell. Okay, it became a text. I don't know. I hit a key that made it into a text, but let's ignore that. But basically, this is now the actual 1 is 9,000. If we change the value here to 2, it will become that one. So actual 1 will get this, all of this. Alright. Coding live is usually longer than just talking, but at least you will get it all. So 1, 2, 3, 4, 5. So now that we have our predicted and now our actual, what are we going to do? Okay. We are going to compare the actual versus predicted, and we'll say find the difference. Okay. So we're going to find the distance from the truth. So there are many techniques here, many approaches. One is we can, give me a suggestion, what can we do here? How will we say that overall our function is accurate? How do we measure its accuracy or closest to truth?
Minimize the difference.
Minimize the difference. A difference of what?
Of actual and predicted.
So minimize the difference of actual and predicted. Okay, now we have, the thing is here, we have 5 actual and 5 predicted. So how do we minimize the difference? Minimize the average, we can do that. Minimize the sum of all. Minimize the squares of it. So there are many approaches, alright? So we'll just keep it simple for this one. We will minimize the sum. Okay? So minimize the sum. Minimize the sum of differences. So what we're going to do is we're going to get difference 1 equals actual 1 minus house 1, and then we're going to absolute it. Absolute. So that it will not be negative. Alright? So we can really get that true difference. Okay, difference 1, okay, difference 2, difference 3, difference 4, difference 5. Actual 2, 3, 4, 5. House 2, 3, 4, 5. Okay, so now that we have all the differences, we need to sum them. So total difference equals, oh my gosh, difference 1, difference 2. No, this is how we really program, but we use frameworks like TensorFlow to run all of this in one line. But today we need to understand it, so we will not do that, or else we'll not understand anything. Okay, so now that we have total difference, we will then say minimize it, right? So we will need to save the values of possible modifier 1 and possible modifier 2 when they are really good, right? When it's the smallest. So we will say total difference, so we'll say best difference if, it's not quite best, if smallest difference is greater than total difference, then smallest difference is equal to total difference. So that will be like our placeholder, and we'll instantiate smallest difference here to make it like 9999999, so immediately be replaced. All right, smallest difference. Okay, and then we'll then say, possible best modifier 1 is equals to P modifier 1, and the best modifier 2 is equals to P modifier 2. So now what we have is every time we have a smaller difference, a smaller sum of difference, we will save our values. Okay? So we will just put this here for now as 0, 0. Okay? So at the end of this function, this loop, we can then print our best modifier, best modifier 2 and modifier 1. Okay. And then at the end of this function, if we did everything right, with me coding and you coding review my code, there's like what, 50 of you, Shadow. It will come out the best modifiers for our data. Okay, this is good. Ready? Let's try it. Okay, from 0 to 10,000, let's see how many. It's a million. What's more than a million terms? Let's try it. Nothing happening. Actually, it's running. But what is 10,000 times 1,000? That's 100 million. This is doing 100 million loops, guys. Not good. So maybe let's change this. Let's change this to we'll just change the range from 4,000 to 6,000 siguro. And then this one from 3,000 to 6,000. And we'll be happy with that already. Alright? That will be our sort of our range. So I will stop this. Okay? And I will run it again. So now instead of doing 100 million, it's around 10 million lang. La la la. La la la. Hala hala. Oh, wow. 599 and 3001. Looks like a bug, no? Can't be right. But anyway, let's try it. That's 599. What's 5,999 and 3001? It already found it. Alright, let's try that. Let's try it then. Okay, insert cell below. Insert cell below. And then we will house price predictor. 5. This one is now this. And this one is now this. And I'll say 1. 9,000. Ah, okay. 2. 14,999. Off by 1,999. 3. 20,998. Okay lang. And then 4. 26997. Ah, pretty close. Huh? And then finally 35 covenant C. 5. So 32996. Alright. So basically, we believe that our code is bug-free. So we believe already that the output here is indeed the smallest difference when you do the sum. Alright? So what did we do here? Okay, let me break this down for you. This is already actually machine learning. We call this stupid machine learning because it's brute force, right? But this is already machine learning. Okay? What are we doing here? Let me break this down for you, the terms. Alright. So first, we have, this is what you call the model. Everybody say model. Okay, so when somebody says to you like, hey, what's your machine learning model? And then you can then say, our model is just linear regression here, which is y equals mx plus b. I don't know why they say this as m. Do you know? Yeah, right? M, slope, that's an S, and then they show it as a W. I'm like,
Magnitude.
something, huh? Magnitude. Okay, somebody knows their stuff here. But why is it, that's magnitude, that's a symbol for magnitude? No? But anyways, if you go around, I got confused about this once because you're presenting like, you say y equals mx plus b, and I'm like, that is definitely a W. Alright? So don't get too confused, that's basically this. So what is, y is the function, the what you return, which in this case is equals to price. Okay? W here, or m, or the slope, is the modifier. Okay? They actually call this, maybe it's because of this, they call it y equals weights, okay, times x, which is your input, right? And in machine learning, they call this the feature, all right? They call this a feature, okay? And then plus b. And in math, we call this the y-intercept, right? In here, they call it the bias, all right? The bias. So y equals mx plus b, or y equals w times f plus b. So this is just basically your model. Your weights times the features and the bias. And what you are trying to learn in a machine learning model is always the values of the weights and the biases. So you already know the features, you already know the x, you already know the y, you have some of the y, given the x, you have some of the y, right? But you are trying to figure out the weights and the biases that when you plug in your feature, your input, that will multiply by the weights and the biases computed by the computer, will yield the closest to the y, which is your intended label or intended output. Okay? So in this case, is our price. So that is the model. Okay? Everybody say model. Model. Okay, good. Model. So that's the model. Okay? Now what's next? This is what's next. What's next is what you call the train. That is called the training part. Alright? The training part is where you train. Each loop of this is what you call a training step. Right? So when they ask you, how many training steps? You just say, in this one, I think I did 1,000 times 1,000 times 3,000. I did 3 million. Sorry, that's 2,000. 6 million. 6 million training steps. Well, if you say that in real life that you did 6 million training steps, most of the machine learning people will be like, what? How much compute do you have? Right? This is because we're only doing one weight and one bias, right? We're only computing one possible modifier, two second possible modifier, which is bias and weight. In machine learning models, usually they have millions of weights and biases. Okay? So when you say 6 million training steps, that's impossible. Usually it's just like 1,000, 2,000, 3,000. Like that, because one training step can take maybe 500 milliseconds, depending on your model or the complexity. All right, but here we're proud to say 6 million training steps. All right, so this is a training loop. Everybody say training loop. Training loop. Okay, another term that they usually say is what they call an epoch. All right, an epoch is basically where you've done enough training steps to go over the whole data set. In our data set, how many data do we have? 5. Very good. In machine learning, mostly you feed thousands, 10,000s, hundreds of thousands of data, right? So you can't do one loop, just one loop, and then input the 100,000 of data there and compute everything all at the same time. You can't do that. You do batching. So another term. Everybody say batching. So you do batching, all right? Batching. So if you have 100,000, you will batch it 100. So every time, if you do a batch of 100, a batch is 100, then every training step you take 100 from your data and then you train on that, and then you take the next 100. And so to do one epoch, how many training steps do you need? If there's 100,000 and 100 per batch, how many training steps do you need to achieve one epoch? 1,000, correct. Because after 1,000 steps, by doing 100, after 1,000 steps, you have done one epoch or one whole, your model has seen the whole data set. So when somebody asks you, how many epochs did you do? I did 5. What's your batch size? 100. You can do it. Why are these relevant? Actually, this is relevant because in machine learning, most of the job of the data scientist is actually trying just to tweak the numbers in the batching and the epoch, like how many training steps. That's all you do really. Oh, why is your model better than mine? I did 6 epochs and batch size of 10. That's why I did a batch size of 100 and 5 it didn't work. So it'll be like that. It's usually like that. Right? It's really like that. It's like your high-level trial and error. You're repeating, I want to train 98. What can I try? Maybe I'll increase the, That's what you do in machine learning, right? This is a new compiling actually. Your boss, what are you doing? You're doing nothing. Training pa, sir. Why is the epoch 100,000? Ay, na-time po. Mapa-moment. Alright, so you have that. So you have the epoch. So training step, epoch, and then batching. So here we don't have batching because we only have 5 data set. Okay. So that's training, epoch, batching. Up next, okay. Alright, here we tried to get the total difference. Alright. Some people call it total difference. I like to call it distance from truth. Okay? Like, more about how far are you from reality? This far. Layuan mo eh. So your distance from truth is like like how far you are from reality. That's what I try to call it. Now, most people in machine learning, the real ones, like the ones who do practice, they call this the cost function. Alright? So in this case, our cost function is what? Our cost function is equal to the sum of differences. That's all we did. Right? Now, some machine learning people will say, what's your cost function? They will then say something like, my cost function is the sum of the squares of the differences. So each difference, they will square it, and then they will have the sum. That's their cost function. So dako na nung kayo ilang cost function? Yes, dako. But they will try to minimize that man. They will try to make that number smaller. So the cost function is actually, doesn't matter if it's big or small. What matters is that you are trying to make it smaller on every training step. Right? So that's basically what they're trying to do, because at the end of the day, you're not after your cost function, you're after your weights and biases. And so when your distance from truth is small, your weights and biases are closer to the truth, basically. Alright. And then there are another term, cost equals sum, or this is what we call the cross entropy. Right? I will show you that one. Okay? Images at google.com, cross entropy formula. Okay? So, this is what intimidated me. There. This is the formula for, right? But actually, the symbol E here, the E, what's that? Summation. See, it's just that. It's just the summation. But when I saw that, I was like, woohoo! That's so scary. I don't even know how to write that, but that's summation. So that's basically it. Cross entropy is a summation of something, the log of blah blah blah. So they just did that. So there are many types. There are many types of models. There are many types of batching. There are also many types of cost functions. So why is this cost function important? Well, some of them have pros and cons, right? So for example, if we just sum like what we did here, the sum of the differences, it can be that our difference from one is very big, right? But because the others are very small, then our cost is small, right? But if we make it a square, right? We square everything, then even if there's small difference, it gets amplified. So you're kind of forced to equalize. Okay? This is what you call linear regression. What we just did is called linear regression. Linear regression, let's see. So if you notice, this is our function. Our function, these are the data. So imagine house price 1, 2, 3, 4, 5. Our line is just the function. Right? And what we're trying to minimize is the cost. And let me just open image in new tab and make that bigger. You see those red lines? Those red lines are basically the differences. Right? And what we are trying to do is either we sum all of these and make sure that the total is smallest so that the blue line is sort of like equally in there. Right? And if you do squares, it might be a little bit better fit. If you do summing, it might lock into like to the majority. So there's pros and cons. I will not dive deep into that. I just want you to learn that when somebody says what's your cost function, it's just basically referring to this line. How you compute your distance from the truth. Alright? And there are many ways. Everybody say cost function. Alright, so we covered the model, the training steps, the epoch and the batching, and we also covered the distance from truth or the cost function. Now, another term that most people will hear is what you call gradient descent. Say gradient descent. Has anybody heard this term before? Do you know what it is? Alright. Today, what we did is brute force. Alright? We determined the weights and biases by exploring every possible combination between 3,000 and 6,000 and 4,000 and 6,000. Right? We explored every possible combination for weights and bias, or for modifier 1 and modifier 2. That is a really bad way of doing machine learning because it will take super long. Right? So what machine learning does is they introduce a concept of gradient descent. Alright? What gradient descent does is that instead of instead of going through every possible combination between 4,000 and 6,000, it tries to be smart about it. And how it tries to be smart about it is that using the difference here, using the value of the current value of P modifier 1 and P modifier 2, it tries to determine the next P modifier 1 and the next P modifier 2 that it will try that will yield a smaller total cost. Right? Now, how they do that, I was absent. Okay? It's actually some calculus stuff. If you want to look into it, it's called the derivative. Now, really, honestly speaking, I was really absent in that. But all I know is that it can measure like that. You see this, oh? You see that line there? That derivative is the cost, so it can tell like where it's headed. So what we want to do with the cost function is you want to make the cost function go down, right? You want to minimize the cost function. So using the derivative, what you do is it computes the next modifiers, next weights and biases that will yield a lower cost function, right? A lower value for that. How it does that will be another talk by somebody else. Okay? Basta mauna siya. So derivative. So instead of doing brute force, gradient descent is then it uses the derivative function to basically predict the next one. So instead of having to go through every possible combination, it then just uses like the next step will be a better one, right? So it achieves minimizing faster, right? Now I will introduce another concept called learning rate. Learning rate. Okay, let me see if I can pull this up so I can have a visual. Learning rate. Here we go. Alright, so this is your cost function. Okay, this blue line is your cost function, and this is the space where you started. Alright? This is the space of possible modifier 1, the intersection of possible modifier 1, possible modifier 2, for example. This is your x and y. So, this is the result of cost function. What you want to do is you want to go here. Right? Now using the derivative, it will go down this space. Right? Now your learning rate is the amount of change that you will introduce so that it will move. Okay, so for example, instead of doing +1, +2, your learning rate will determine if it's going to do +10, +20, right? Because for example, going back to our example here, we're doing +1 here, right? +1, every time we do a train step, we do only +1. But if our value is going to be 1 million, like the actual weight that we need to get is 1 million, it's going to take forever to get there. Okay, by forever, I mean like 999,999. But with the learning rate, we gradient descent, and we already know the direction. With the learning rate, we can say, hey, instead of doing +1, do +10 or +20. So you advance faster toward the right direction. So when your learning rate is too low, like +1 for example, it'll be like so slow, and you might never reach the bottom. You might never reach the minimal value. Okay. If your learning rate is too high, you might overshoot. Okay? So if the value of the cost function is here, this might boom, I don't know, like you would even go out, right? Okay? And then if your learning rate is perfect, it will go just right. So how do you know what is the right learning rate? Aha. So, trial and error. Okay? Now some data scientists have been trying to be smart about it. So what they do is what they call exponential decay or decaying learning rate, for example. So they start out with big values, and then every training step, they're decreasing it by half. So that as they come, they start out fast going to the right direction, and as they are closer there, they decay it slowly. So that you are moving slower as you are moving closer. Right? Some success there. There are also some pros and cons. You can look it up. Okay. Another way to think about it is imagine if you are the cost function yourself, right? The cost function space is a mountain. It's two mountains, right? Just like your mountain here, your mountain here. You're in one mountain, your goal is to go to the valley or to the bottom of the mountain. And you're wearing super boots. Right? Your super boots is that every time you move, it will amplify your step, right? So you can adjust it. If you make it slow, or like normal, turn to normal, just 1. So every step you take is 1. You will take forever to get down. If you increase it, your super boots be like maximum setting. Every time you take a step, you're in the other mountain. Right? It's like, whoa, I wanna go down. You just, I wanna go down. Like you can never go down. Because every time you take a step going down, you overshoot and get to the other side of the mountain. Right? So you have to set it just right so that on your first step, it'll be like, whoa, okay, closer, and then decrease. Whoa, okay, and finally it's just one step na lang, so you're like, okay, I think this is the lowest spot already, and we've reached the bottom and minimize the cost function. Alright? So that is how you sort of adjust the learning rate. Okay? So that is the concept of learning rate. So now that you've seen this house price, and then you've seen this data, the thing is, I lied to you. That's actually not really the real, rooms is not the real predictor for price, right? Well, kind of. It's not the only predictor for price. What's the other predictor for price? Location, right? If you're in Cebu Business Park, yeah, right? But if you're in Barriolus, it's like, it's just not really location, sort of, it's like, it's district, no, or something. What else? Size. So this is a lot area, and there's even the size floor area. What else? Sorry, what's that? Features, amenities, and daily. Why? I got confused there. I don't know what you're talking about. I think it must be a Lexmark thing. Amenities, what else? Age of the house. Huh? Or years since last renovation. Right? What else? Previous owner? Previous tenant? Yeah, what if it was the president there, no? Dating bahay ni ano, ni Anilio Aguinaldo. Museum. What else? What else? Furnishings. Okay, and there's many more, right? So, or this stands to BRT proposed. What's that? Alright. This stands to proposed third bridge. Actually, there's construction, so that one's more of like closer to reality.
Bathroom.
Okay, my wife said bathrooms, and we have to add up. Bathrooms. Alright, so that's number of bathrooms. Okay, so there's many. Alright, there's many. Now, what you have to do as a data scientist usually is you have to get data that has these. Right? So when you look at house pricing, for example, I'm like, okay, my boss told me this, so I'll be like, Google house pricing data. Be like, oh, data. Oh, Kaggle. Okay. So this is actually a machine learning community or artificial intelligence community. Feel free. It's like the GitHub for machine learning models. So they have data sets there, models there, so try it there. So let's do data. Blah, 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 blah. So here, what they have, let's see. The data feeds that they have the selling price. So this is good because they have the price. You can't trade if you don't have the price. Okay, we have the building class. I don't know, here we only have class. I don't know if your class. Zoning, lot frontage, lot area, street, type of road access. Wow, this is very comprehensive. Alley, type of alley access. Ito, adali, alley lang yung tanan. May nag-alley. Lot shape, land contour, flatness of the property. Diba? Pang-pang na, mahal man siguro pang-pang din, no? Maria Luisa, Malgayo. Utilities, lot configuration, land slope. It's different from lot contour. Okay, that's different because slope is consistent. The lot contour, what if it's like that, right? Okay. Neighborhood. Okay. Condition 1, whatever, building type. So there's many. This is good. Alright. So, wow, that's a lot. Wow, that's not even. Okay, so there's a lot. So we can download, for example, we can download all this data. Or we can just see here if we can. Okay, but you're letting me register. An X button that doesn't work. UX people, tell me about this. Alright? But basically it's there. So we can use this data, right? And we can base it off that. Now, the first thing you need to do as if you have that data, say we have that data. First thing you need to do as a data scientist or machine learning person is to figure out which features are actually related to the price. Because remember, you're trying to figure out the price. And some of the features here don't actually relate to the price. For example, let's try to find one. Trying to find one. Foundation. Nobody cares about foundation. Basta nagtindog na, muna na. Okay, maybe. Heating. In the Philippines, we don't care about this. Everything is heating, right? So we don't need this data, all right? So this is what you call in machine learning as called as feature selection. All right. Data scientists spend a lot of time, trial and error approach actually, in some degrees, feature selection where you're trying to get the correlation of a certain feature and how it affects the price. Because usually, what affects the price is a combination of all these features, and some of those features are irrelevant. So you're sort of like taking away some of the things that don't matter. So that's the first one. Okay, so feature selection. The next thing we need to do, the problem now is how do we enter it here? Okay, so we have to pass through. So for example, let's select two features lang. Let's select the number of rooms and what? Bathrooms. Okay, rooms and bathrooms. Okay, so we're keeping it simple. We're just saying the rooms and the bathrooms is what we haven't even put in the kilometer distance from the BRT or from the new bridge. We haven't put that. Just this one for now. How will we modify this function over here? Okay, how will it become so that we get the price? Because our function right now is like this. This is where I think machine learning actually really shines. All right, we can modify this function called by doing this. Have you heard of matrices? Matrices. All right. So what we will do is we'll pass rooms, bathrooms. Sorry, that will be our x. All right, and x will be multiplied by the modifier plus the modifier 2. Okay. Now, when you do matrix multiplication, what happens? Sorry, Let's make this a matrix. Modifier equals modifier is equals to modifier. Why is making it like this? When you do matrix multiplication, what happens? Matrix multiplication. It follows the shape of how to multiply matrices. Kisay absent ani. Taas ka mo. Away mo amin, no? Geniuses. Alright, we'll try it, okay? Because honestly, I was absent on this one. Or I was there but closing my eyes. Alright? So a matrix is an array of numbers. Okay? N dimensions. In this case, it's two-dimensional. Matrices are two-dimensional arrays. Alright? So you multiply by doing that. Alright? Blah, 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 blah. But the interesting about the matrix is that the output shape follows the shape of the columns and the rows of the features, or the, what do you call this? What you're multiplying it with. So we can actually change the shape of a matrix based on the shapes of what we multiplied with. Verse isa. Matrix multiply calculator. May naki mag-google na nato ba? I just want to show this to you. So the matrix dimension A is 1 by 1. So in this case, we have how many features? Rooms and bathrooms. So 2 by, I think 1 by 2. Let's try 1 by 2. I think it's where. Matrix B is just 2 by 1. Okay. So
1 by 1.
You can't multiply man hindi the same. May error niya siya. It has to be basta ang column mo ang row pareha dapat. If you want to learn about matrices, Google it. Okay, so for example, our number of rooms will be 3, our number of bathrooms will be 2. Okay, we will now have to have modifier 1 and modifier 2. Okay, so let's see, 2 and 2, for example. Let's see this, calculate. What will be the result? So now you have a 1-dimension matrix. Alright? How did that happen? Kanina to. Matrix is fun. Alright. So what you do when you multiply a matrix is you basically multiply all of these by all of these, and then you sum it, and then you get it here. Alright? So we multiply matching members. Now see, you sum it up. So blah 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 blah. So 1 times 7, 2 times 7, 3 times 7, and then you come up with that. So that's how you do it. I'm not going to talk about matrices. Alright? This is a different topic that you should have attended in college yourself. Okay? On your own. My point here is that with an input of 2, okay, we can come out with an output of just one size. Alright? So what we need to do here, we just it comes out as 1 here. Wala na. But anyways, okay. So in here, rooms, modifier 1, 1, and modifier 1, 1, 1, 2. Okay, so what we do here instead is we tell the computer, we tell the function that instead of just looking for one modifier, he has to look for a modifier matrix. Alright? That when multiplied by the matrix of rooms and bathrooms will yield the price. When after added with the modifier 2. So it now has to find 3 things. Right? Modifier 1, modifier 1, 1, modifier 1, 2, which is actually just a matrix. Right? It also has to find the value for modifier 2, which is our bias. So that when you add all these things together, you yield the price. So when we just add more features, so rooms, bathroom, BRT distance, I really love the BRT, no? Amenities, count, for example. Okay? So when you have all these 4, this becomes BRT and amenities. Then you just have to increase your matrix size as well. Right? So now your computer is now also finding out many what do you call this? Modifiers. Now, take it one step further. Hold it in your brain. Okay? Take it one step further. How do they do it with images? Okay. Images have pixels, right? So a 28 by 28 image image has how many pixels? 28 by 28, 724. So it has 724 images, pixels. So you just have pixel 1, pixel 1, pixel 2, pixel 3, and then over here you have pixel 1, pixel 2, and then over here you have modifier 1, modifier 2, modifier 3, one each for each pixel. Right? So then what are you trying to guess for that? You can then make the computer guess whether it is a number 1, what number it is based on the image. For example, if you have pictures of, or if you have pictures of me and Nielsen, right, and the pixels, then based on the number of pixels, based on the weights and the modifiers, it will yield 1 or 0. And the value would be 1 if it's Nielsen, 0 if it's Albert. Something like that. Okay? So that's how it flows through it. So what I've explained, I've taken you from the concepts of machine learning, the models, the training step, the epochs, and the cost function, down to how you do it from linear regression and how you expand that. Okay? How do you expand it and how you advance it to then having multiple features. So instead of just having rooms, you have rooms and bathrooms. Okay? So then you just increase the number of features, still keeping the same function. If you notice, we haven't changed our function here. It's still y equals mx plus b. But instead of doing y equals mx and x is the value of just 1, x is now the value of a matrix. Right? And then plus b, which is also a matrix. It could be one dimension, it could just be one value matrix, or it could be an array as well. Okay? And then we've done it with an image. An image is a pixels, right? So we just have 728 features for 28 by 28 image. And then we have a 728 length matrix array as well. Alright? Now what if it's a colored image? It's 28 by 28 pixels, but it has RGB layers. Diba? It's 0255 intensity. I don't know if you guys are printer folks. I mean, so I know how to explain, I guess. But 28 by 28, so you have 3 layers, RGB, or maybe in your case you have, of course, CMYK. I don't know if it's, I don't know actually, maybe I'm making fun of myself. I don't really know what I'm talking about. But maybe it's okay, fine. 3 layers, RGB, I'll stick to that because I know that one. RGB. So instead of having a 2-dimensional matrix, you now have a 3-dimensional matrix. Alright? You have your array, your pixels, and then you have RGB, so 3 layers. So you have a depth of 3. So instead of your modifiers or your weights and biases just being a matrix of 2 dimensions, it's now 3 dimensions as well. So now the computer, instead of just having to find one weight and one bias, it now has to find the 3-dimensional matrix and the combinations of all those values. Okay? So if we were just doing brute force, it would take a long time. And that's exactly the reason why back in the day when they had these ideas of artificial intelligence, it didn't pick up. Because they didn't have enough compute processing power to do all these. And with the advent of gradient descent, where you don't have to brute force your way through it, and then the computer is being faster now, it's now possible. Because the computer can now find a large number of matrices, or a large number of 3D matrix, the values for that, in much quicker time, even if they're very big. Now, with video, and the lady over there, what do you have? You have time series data, right? You have, what is a video? It's a series of pictures with time, right? You have frames. So you have one picture is a pixel, RGB, because it's colored. Who does black and white? Colored. So you have 3 layers, so you have a 3-dimensional now. Then you have time series, you have time, so you have a t value. So now you have a 4-dimensional array. So now, 4-dimensional array, a 4-dimensional matrix. That's then what you call, then you have to have a 4-dimensional value for your weights again, right? So now, it's much more numbers. And 5 dimensions, and 6 dimensions. And actually, for translations, for example, for like words, they have like 500-dimensional embeddings that they do. Or 500-dimensional arrays. Just a term. They will say something like here. They will call tensor. Okay. What is a tensor? A tensor is actually just an n-dimensional array. I like to call it array because we're programmers. Okay? Someone will say n-dimensional matrix, n-dimensional, so in this case, it's just n-dimensional, meaning a tensor could be 1 dimension, just one value, 2 dimensions, a matrix. It can be 3 dimensions, and then 4 and 5 and so on, 6 dimensions. So you have, that's what you call tensor, and that's why TensorFlow, the framework, is named TensorFlow, because it's just tensors and the data and the numbers flowing through it. Wow. Alright? So that's why you have tensors. Okay, so now that you have that, nag-nosebleed ng uban, alright? But I hope that we've taken you from the basic of machine learning and given you taste of advanced. Alright? Now I'm gonna do some demos for you. You guys ready? One na. Are you guys ready? Okay, thank you. Any questions before I go to the demo? Any question on this? Any question? Can you repeat everything? Are you serious? Okay. Did it make sense to you guys? Alright. I was a little bit concerned. Joke ka, ha? Okay, so let's go ahead and do some demos. Let me find my demo set here. Okay. The first demo I have is basically we're gonna play Pac-Man. Alright? Yay, lingaw sila. Okay? We're going to play Pac-Man. And what this is doing behind the scenes, what it's just really doing is we're using the same concept with the machine learning, turning pixel data, which is we get from images, like right now. Okay? So, why am I doing that? Okay, so what we're gonna do is we're gonna tell the computer that, hey, take note of this picture. When Albert has that face, turn left. Alright? And let's try for the right. For the right, I'll be smiling. Okay. Albert has that face, turn to the right. When it goes up, what will be Albert's face? Shocked. Alright. Okay, we're shocked. How about going down? Sad. Okay, this one's angry. So sad. It's so hard to be sad. The yuho ka daw nanin. Another one. Just normal. When it's scary face down. Usually that's my normal face. Alright. Now the computer can't really learn so much if it's just 4 samples, 1 of each, right? We need to give it more. So I'm gonna give it about 100 of each. Okay? So please stay calm while I concentrate. Alright, so angry. Okay. I've embarrassed myself in front of you. Smiling. Okay, 111. How about shock? Oh, this is gonna be long. Right? Okay, shock face. Now the serious face. Hala, one new word. Okay. Enough. Alright. So we have to train this. We have to still train it, right? It will use this as the images data as training, and we have to set the learning rate. Okay, we'll set it to 0.001, not too big. It should be a value between 1 and 0. Batch size 0.4. Let's see, with 20 epochs, hidden units. Hidden units is like, actually I forgot to talk about that. Neural networks. Sometimes, when you have this, what they do is they layer it on top of each other. So instead of, before returning price, what they can do sometimes is they can say the output of this device is y equals mx plus b. What they can say is z equals, and they replace this one. What they'll do is they'll replace it here, and they'll make this y. And this is modifier 3, and this is modifier 4. So they sort of like layer it on top of each other. Like the output of 1 is before. So this is now deep learning. Everyone say deep learning. Deep learning is just machine learning models stacked on top of each other. Right? That's what it is. Okay, and we can go very deep learning. ZZ equals, and then you just replace that Z over there, and this modifier 5 and this modifier 6, and these are still matrices on its own if they were matrices. So it can be very quickly very many weights and biases. So that's deep learning, and they can go as many deep. So for example, with Google's Inception, it has like 20 layers of that. Each one has slightly different model, where the shapes of the matrices are slightly different. But enough of that. Let's go back to Pac-Man. Okay. So we have Pac-Man, let's play, let's train. So it's training now, and it will now say the loss. The loss is the cost function. The loss is the output of the cost function. Alright? So the loss is 6. It's not doing so well. Maybe let's change the learning rate. There. So nag-ampak siya. Okay? So now, okay, that's a good loss. That's a very small loss. Now, let's play. Let me try to remember first. Shock face is up. Angry is left, smiling is right. What's that face? Normal face is down. All right, I'm gonna suck at this. All right, so we have that ready. All right, shock. Oh no, what's right? Smile. Let's test it. Okay, another one. I want to go left. Left. Again, last.
Down, normal.
Does anybody want to play? They're like, nah, not like that. Later. Alright. So see, if you notice here, it is able to identify. So I'm like mad. I'm like happy. Okay, you see the highlight? And then shock. Bati, ganing kwa, normal face. Like my normal face looks like everything else. My computer can't figure it out. It's like, I don't see the difference. The normal face seems like you're doing something. Alright, so there's that. Okay? So behind the scenes, it's just translating the images into pixel data, which is just numbers. It's a matrix of RGB. And then training that against, so that when you're fed new data, and when that new pixel data, the pixel shape is given to the function, it just multiplies it against the same, or runs it across a formula of the same weights and biases that it was like, it found it was the best, right? Like our best modifier 1 and best modifier 2. So for that, the weights and biases that were the best, it runs it that and gets a prediction. And the prediction in this case is just left, right, up, never mind, up and down. Alright, so that's basically what it is. In applications, then you can have games like this, where you make people make fun of themselves. Alright, another one. This one is a little bit less, similar concept actually, but less intense. Okay, not so scary, not so pressure also for me. Okay, let's go. So what you do is we just
experiment that lets you explore how machine learning works.
Yeah, I know. Okay, so what we do is we have the input, and instead of making faces, because there are faces, we'll put my hand in there. So if I just put hand, okay, so I put hand like that, right? So that will be green. Okay, so I'm getting 100 of these ones, all right? So that would be the output. If we have the hand, the output will be the cat waving, all right? The next one, what is this? We'll see. Okay, this one I put my body. Oh, that one. My body. My body is there with my logo, the Google Cloud logo. All right, there. So that's. What happened? No butt. You have questions? So how would we transform the value of, let's just say, Lexmark employee? I can't think of anything else. And normal person. Okay. I'm not saying that Lexmark employee is not normal person. Non-Lexmark. Okay. So what you do in one-hot encoding is you convert it into this, where you say Lexmark employee is equals to 1, 0. And then a non-Lexmark person is 0, 1. Okay, and why that? Why can't it just be 1 and then the other one is 0, right? Why can't it be that? The reason for this is because when the output of your system usually looks something like this, the computer can't guess for sure. It will have a value between 0 and 1. So it will actually be like this, 0.998, and this one is 0.002. What do you think it's trying to tell you? It's showing you that it's predicting a Lexmark employee, but with like 99.8% confidence. That's basically what it is. Alright? And sometimes the value will be like this. It will rarely be like this actually, but you get the gist. It will be somewhere in the middle. It'll be saying it's 50% confident on any of that. Alright? So that's the output. So for example, when you are doing 3 values, so for example, let's not do Lexmark employee anymore. Let's just do t-shirt, for example, just random stuff. Shoes, and then dress. Okay? Then you make 001 here. And it will be like that. So that would be like a one-hot encoding. It's a numeric value, but it's represented into like it's like a vector. Vector as an array. Okay? And then the output will look something like this when it's trying to classify something. 0.9, 0.01, 0.09. It will look like that, right? When you do the output. And then you can say, oh, let's look for the highest value there. And then, oh, this is a t-shirt. Like that, when you convert it back. Right? So that's sort of how you change it. Now, what they also do, and I'll just jump in a little bit, taking a little bit step forward. If you're doing words, like a lot of words in the dictionary, like 27,000, for example, they use different techniques for this one, not like this. They call this embeddings, or instead of just having one dimension like this, what they do is they can have multiple dimensions. Alright? So this is an n-dimensional array, for example. So n dimension, you can have like 500, 1,000 dimensions. Right? And what they do is they position the word. So you have 0, 0, 0, 0, 0, 0, 0 in all the spaces in that matrix, and you have just 1. Or else it would be a super long array, right? So what you do is you squeeze that array into a multi-dimensional matrix so that you then only have the value of 1 just somewhere there in the middle. Right? And then what you can do is you can take a book, a series of books, corpus, or train data, and what you can do is you can compare the words. You can scan out the words, and you can then determine that put the words that are closer to each other. For example, if amazing and awesome always are close to each other, then put them near each other in that matrix, in that like the n dimension, whatever. So then you have related words clustering together, and based on not based on their meaning, but based on their proximity in data in real life, right? So that's how they use synonyms and how related words are, and that's very close to what they use for autocomplete. Right? So what this example you do in autocomplete, they scan all the text messages, and they try to predict the next word based on the occurrences of this next word, the distance of that word, the presence of those words in words previously typed. So when you're typing something, they try to predict which are the closest words in this network, and the next. Right. Okay, so now we're back. Let's have some fun. Okay. So we have t-shirt. Oh, I need internet. Okay. We will look at Nelson's password. Alright, so okay, so we have this. I have to train it again actually, guys, because I think we have to redo it. Skip the tutorial. Alright, we train green by putting the hand. Alright, so we have the hand is training. Hello. Okay, then we have 100 of these. And then we have the body. My body. Yeah. All right. Okay, and then that's what the output. Okay, so we have the hand. See, this is using training already, right? And the third one will be just the absence of it. Oh, the absence, the hand, but this one's the absence of it. Okay. All right. So that one is on, and then you can put in the body. Okay. And you have that. All right. So what is this useful in real life? Well, real use case. So for example, in our company, we used to run a dating app. We built a dating app, and one of the problems we had with the dating app is that a lot of times, users tend to upload like pornographic images, right, as a profile picture of themselves. So what we did was we had a system where every time somebody uploaded a new profile picture, it would come out in our chat group, and we made it that there's buttons if it's explicit or not, right? So we get to see everything, right? So sometimes we're even like, oh, is this explicit? And we're like, madada pa ba ni? So we became the judge, and to be honest, it became stressful after a certain time, right? Because we're like, oh my gosh, like, why don't I have to see this? Why do I have to see this, right? So what happened there is what we did is you can train it, you show it enough of this data, and it's able to decipher, okay, this is not to be in the system, this is to be in the system. So now, let's get this done. Now, without having to look at it, we now have an AI looking and doing all the, the screening, right? And when the confidence level is low, we can then just target it. It will go, and it will send us sort of like flag it, and we can do a manual review. It's never seen this before. I'm like, oh, okay, that's a person, yeah. And put that in. All right. So yeah, that's basically it. Any questions? So that's our demo, and any questions? I can take maybe like minutes for questions. 2 minutes for questions. Any questions? Yeah.
You said you have worked with the Office of the President.
Machine learning. Okay, go on.
What types of machine learning or AI programs?
Okay, it's a very interesting question. First, with the Office of the President, the World Bank. The World Bank lent the Philippine government a lot of money, billions, to build roads in far-flung places. Right? The money has all been spent. We're not sure if the roads are there. So it's very difficult to go and inspect physically because the inspector goes there and then there's war going on. So somebody's like, oh my God, hindi tayo makapunta doon. Like, huh? Ito na yung report, oh. May pictures na yan. Like, so it was very difficult to physically inspect the actual roads. So what they did is they required all the contractors to submit pictures of the roads. Geotag pictures, so you have pictures of the road, the location. So we ended up with hundreds of thousands of images. I think around 200,000 for the first batch. Our job was to classify whether these roads were concrete, gravel, asphalt, the quality, the width. We were like, yeah, let's do this. We hired an army of interns. I don't know if some of the interns we have here are participating in that. But we were like, I think we had 12 people just going over it. We made a tool that they could easily classify with shortcut keys, right? Concrete. So that's what they did all day. At the end of a week, we were only at 10,000. So this was not working, this was not good. So what we did was we used this 10,000 images, used as training data for a model that can classify whether a road is concrete, gravel, asphalt, or dirt. And then we ran the rest of the 100,000 images through the model. And so very quickly we were able to get a report of how many were concrete, how many gravel, how many asphalt, and how many were selfies. Right? Like selfie with the inspector and all these things. So we were able to quickly determine that. And the project, instead of running for months, we were able to cut it down to 2 weeks. So that's basically one of the things that I think highlights the project. Thank you for asking. Any other question? Okay, I think my time's up. Feel free to message me on Facebook if you have any other questions. I'm Albert Padin on Facebook, so feel free to look for me there. Just say that we met at Lexmark. And I'm also hanging around for a few more minutes, very few more minutes. I need to go after, but I'm free to answer any of your questions. Thank you guys. I hope you had fun.